Hi, this is Chandrakant. Today we are going to discuss a very important concept which related to the steady state voltages across the capacitors when the equilibrium is disturbed. Okay. Uh, Quite recently questions are keep coming in the competitive exam, and also to understand the basic concept of the capacitors connections and charge distributions. So we are going to discuss the three cases in general. Let's begin. In case 1, you can see here that a DC voltage V connected through the resistors and capacitors through a switch, and the switch is closed at t equal to 0. Okay, and the initial voltage across the capacitors is V0. So our concern is find the V infinity, that is the steady state. After the switch is closed for the long time, what will be the voltage across the capacitors? So you can easily see that regardless of the initial voltage across the capacitors, at the steady state, capacitors will be completely charged to whatever the voltage, forcing voltage or forcing energy source is this voltage value V, and that will be forced into the capacitor. So you can say that capacitor is charged to or fully charged to the voltage V regardless of the initial voltage, because it is a single capacitor. Obviously it will be charged fully. In the same case, when you have initial charge across the voltage is your Q0, and that is the initial voltage V0 is equal to V0, that is V0 is equal to, that is Q0 upon C. Okay, so when the switch is closed, so capacitor will start discharging across the resistor, through the resistors, and finally at t equal to infinity, so your VC infinity, that is when t tends to infinity, or steady state value will be simply 0, because the single capacitors and the capacitors are fully discharged. So this is very simple case, but situation changes drastically when we have two or more capacitors. See the situation here. The qualitatively, what happens here, when the capacitors, when the switch is closed at t equal to 0, capacitors, one of the capacitors, or you can say the voltage start, if the voltage is greater than the summation of the two voltages, so it will charge. Okay, and if the voltage is, the applied voltage is less than the summation of the two voltages, it will start discharging and ultimately find a equilibrium. So in this case, what you will do, you can write the normal KVL, KCL, or you can use the Laplace transform method to find the current, then t tends to infinity or like that, or you can find the transfer function or in the S domain, then use the final value theorem to find the steady state value. But how we can find intuitively the steady state value VC1, VC2 as t tends to infinity? I mean, after a long time switch has been closed. So very simple way is the C. When I close the switch, what happens? Capacitors, either both the capacitor can be charged or discharged, and the charge flowing through both the capacitor would be same. So one thing I want to, before proceeding, one thing I want to discuss, that is when you have two capacitors C1 and C2 connected to a voltage source, I assume that there is no initial voltage across the capacitors. So what will be the steady state value Vc1 and Vc2 when I applied the DC voltage of V volt? So very simple is, we know that C1 equal to Q1 upon Vc1, C2 equal to Q2 upon Vc2, right? So we have C1 upon C2 equal to Vc2 upon Vc1. To add 1 both the side, so you have C1 plus C2 upon C1 is equal to Vc1 plus Vc2 upon Vc1, but Vc1 plus Vc2 is equal to applied voltage V, so Vc1. So from here, this is C2. From here you can find that Vc1 is equal to C2 upon C1 plus C2V. Similarly, you can find Vc2 is equal to C1 upon C1 plus C2 into V. Having learned these things, let us move to our original questions. Let's say this change in voltage, okay, the change in voltage would be, total change in voltage would be del V, right? Initial voltage across the capacitor C1, you can see here, initial voltage across the capacitor C1 is equal to V1. Initial voltage across capacitor C2 is the V2. Now we have after the switching, we have a change. Obviously that change will be equally across the, that means the change in voltage may not be equal because the capacitors values are different. Let's say some changes takes place, that is the overall change in voltage is the del V. Overall change in voltage is the del V. Okay. There is a change in voltage when the switch is closed. For the first case I am considering, when switch is closed, the overall changes in voltage across the both the capacitors is the del V. Okay. Now I have calculated these values when the capacitance are different. So that change in voltage I can write like this: change in voltage for capacitor C1, or I can say del V C1, which is equal to C1, because it is a del V C1, that is for change in voltage for the C1. So del V C1, okay, that will be the, see here equation, C2 plus C1 plus C2 into del V, because this is the overall change across the both the capacitors. And similarly for change in voltage for C2 will be the C1 upon C1 plus C2 del V. You add together, obviously del V C1 plus del V C2 is equal to overall change across the both the capacitors. You can add and you will find same del V. Now come to the, because we have also initial voltage, okay. So for C1, it is, for capacitor C1 the voltage will be the V1 plus del Vc1. For C2 the voltage will be the, this is a steady state value, okay, V2 plus del Vc2, okay. But these overall changes will be equal to the applied voltage. That means V1 plus del Vc1 plus V2 plus del Vc2 is equal to applied voltage. So put these values, del Vc1, del Vc2. So V1 plus V2 plus this is your okay, del Vc1 del Vc2, which is your del V. Okay, del V is equal to V, right? So your del V is equal to V minus V1 plus V2. Once you find the del V, you can put these values and find the individual. And for this case, for with initial voltage across the capacitors but without any forcing functions or voltage. So same process you will follow for this and this, same process you will follow, and here what we will do, that is your this V1 Vc1 del Vc1 and V2 plus del Vc2 equal to plus 0. Here we have done the for V, but for that case, that is V1 plus V2 plus del V equal to 0, or del V is equal to V1 plus V2 minus, I mean to say. Okay, and relatively you will find out. Okay, we'll move on example. Let us consider the case here, 2 microfarad, then here we have 3 microfarad, right? And this is the initial voltage, let's say 10 volt. This is, we have initial voltage of 2 volt, and switch is closed. What will be the steady state value? So let's say del V. So del V we found out, that is a minus V1 plus V2, that is minus 10 plus 2, that is minus 12 volt. So as for the this, so this is a C1 and this is a C2, so VC1 and VC2. So VC1 is equal to V1 plus C2 upon C1 plus C2 into del V. So 10 minus C2 is the 3 upon 5 into 12, that is 10 minus 3 into 2.4, that is 10 minus 7.2, which is how much you get, that is that you get your 2.8 volt. Then VC2 will be the V2 plus C1 plus C2 del V, that is V2 is equal to initial voltage 2 volt minus C1, that is your 2 upon 5 into 12, that is 2 minus 2 into 2 into 2 minus 4.8, that is obviously because they are both in parallel now after the switching, obviously you will expect the minus 2.8 volt, minus 2 point, because obviously they are in parallel na. If I draw like this, two capacitors, they are in the parallel. This is your C1 and this is C2. We are measuring like this, VC1 and this is your VC2. Obviously they will be in the parallel and they have carry the equal voltage. Okay, I have done for the general case. Sometimes you will have the capacitors, one capacitor is charged, one capacitor is not charged. Same way you can do like this. In case of here you see the change in voltage for the C1 V1. Suppose it is charged to V1, suppose V2 is the 0, so 0 del V C2. Simple. Hope you understand. Now come to the net. That is a case when the three capacitors are connected. Just extend it. If you know the very basic things, C1 equal to Q1 upon V1, C2 equal to Q2 upon V2, C3 equal to Q3 upon V3, because both are in the series. Q1, Q2, Q3 equal to, all are equal, right? All are equal. So 1 upon C1 plus 1 upon C2 plus 1 upon C3 is equal to V1 plus V2 plus V3 upon Q. Okay, which implies C1 C2 C3 upon C1 C2 plus C2 C3 plus C3 C1 upon V1 plus V2 plus V3. I want to find out the V1. Okay, so I in place of Q, because Q all are equal, so any variables V1 V2 V3 you can find out. So for Q, first case I want to find out the V1, so C1 V1, C1 C1 cancel, which implies your V1 is equal to C2, and this all together is your applied voltage. So C2 C3 upon C2 C3 upon C1 C2 plus C2 C3 plus C3 C1 and your V. So same way you can find the V2, which is C1 C3, because the component you are finding, you don't have any capacitors in the numerator. That value of capacitor is the missing in the numerator, and this is the summation of Ci Cj for I or I not equal to j, and V3 is the C1 C2 summation Ci Cj, same I not equal to j. Okay, so very simple, you can find out. And obviously if you have initial voltage, so equate it to the applied voltage, like V1 plus del Vc1 plus V2 plus del Vc2 C2 plus V3 plus del Vc3 equal to, if applied voltage there, equal to V. If applied voltage is not there, equal to 0, then find the your del V as usual and find the individual voltage as per the this. So hopefully you can do the questions related to any form of the questions appeared in the series combination the capacitors. Another thing I want to say, suppose you have another branch of the capacitors like this. You have one capacitors branch here, another capacitor branch here. Same process, whatever the process you are applying here, because this voltage is same, so same process will be applied through the same these branches, C1 C2 and C3 C4, and individual voltage you can easily find out, there's no worry. And you have Brahmastra also. Suppose anything you find that it cannot be done by this straight approach, the Brahmastra is simple. Vc1 Vc2, okay, or plus minus V. So simply transform into the Laplace transform way. So V upon S, let's say initial voltage Vc1 0 equal to V1, Vc2 0 is equal to V2. So you will do Laplace transform. So this is the polarity. So as you know, voltage transformer will for this one V1 upon S, and this capacitor C1 will be the 1 upon C1s, then V2 upon S, then this is your C2, so 1 upon C2s. This is your VC1s, and this is your this is your VC1s, and this is your VC2s. And do the analysis as per the, you will find an algebraic equation, then do the partial fraction, then you look at the transform pair, Laplace transform pair table, and then find the time domain. Instead of doing this, suppose they have been asked the steady state value, then you use the final value theorem. Final value theorem. What final value theorem? Limit x tends to infinity, fx is equal to limit s tends to 0, x tends to 0 s Laplace transform of fs. So all this about the initial voltage or steady state voltage across the capacitors. Hope you understand and you can apply into the competitive exam.